Colors in the world of mathematics are specifically what we call the graph coloring. Yes, graph coloring is the colors that also brings life to mathematics. We may encounter a lot of colors in our everyday living, but graph coloring is a unique way of helping us to solve and analyze problems. How about questioning ourselves? How does graph coloring apply? How can we use it? When did it start? What is the main idea of the graph coloring? But first, let's talk about the graph theory in which the graph coloring started. Graph theory is used to find the shortest path in a road or a network. For example, in Google Maps, various locations are represented as vertices or nodes, and the roads are represented as edges, and graph theory is used to find the shortest path between two nodes. So, basically, graph theory is finding the most possible, shortest, fastest, and easiest way to solve a problem to come up with a solution. Just like you were stuck in the traffic, to come up with the fastest alternate route to go to your destination, you're going to get your phone and ask Google Maps what is the fastest or alternate route to avoid being stuck in traffic. With the question of, when are we going to use it? Are we going to use it in finding the shortest path from one point to another? Or coloring a specific object or thing, or what we call the painting, for it to look more beautiful to our naked eye? Or knowing each country's boundaries for us to know where we came from? These examples are real-world situations that graph coloring can be possibly used. But let's focus on another question. What is graph coloring? Graph coloring is the one of the most well-known problems of graph theory, which also can be a real-life problem, as people became familiar with applying tools of graph theory to solve real-world technological and organizational problems. New chromatic models emerge as a natural way to deal with many practical situations. Can you imagine that graph coloring comes from a letter then became an unsolvable problem way back then? And would you believe that the theory was generated from a piece of writing? It seems to have been mentioned for the first time in writing in an 1852 letter from De Morgan to Hamilton. Nobody thought at that time that it was the beginning of a new theory. The first proof was given by Kempe in 1879. It stood for more than 10 years until he would in 1890 found a mistake. He would prove that 5 colors are enough to color any map. The 4-color problem became one of the most difficult problems in graph theory. Besides coloring, it stimulated many other areas of graph theory. Generally, coloring theory is the theory about conflicts. Adjacent vertices in a graph always must have distinct colors. They are in a permanent conflict. If we have a good coloring, then we respect all the conflicts. As you can see below that this coloring has a good coloring because each vertex or layers of the drawing are proper distinctively colored. If we have a bad coloring, then we have a pair of adjacent vertices colored with the same color. So what you can see, the snake was colored with each vertices the same color. Graphs are used to depict what is conflict with what, and colors are used to denote the state of a vertex. So, more precisely, coloring theory is the theory of partitioning the sets having internal irreconcilable conflicts, because we will only count good colorings. We're going to talk about the 3 basics example of graph coloring, which is the edge coloring, face coloring, and region coloring. So we are going to talk about the edge coloring. An edge coloring of a graph is a coloring of the edges of the graph, such that adjacent edges or the edges bounding different regions receive different colors. An edge coloring containing the smallest possible number of colors for a given graph is known as the minimum edge color. For this example, each edge must be counted to know the minimum edge coloring. If you are going to count each edge from left to right, we'll come up with the first one for having 7 minimum edge colors. The next 3 have a 4 minimum edge coloring. Let's talk about the face coloring. The idea of coloring the faces of a map is to assign each face of the graph a color in such a way that two faces that share an edge must get different colors. Faces that meet only at a vertex are allowed to be colored the same color. In addition to general colorings of a map, mathematicians are interested in colorings that use the minimum number of colors. Coming up with this example, the main goal of the face coloring is the assignation of what color are you going to use to color each vertex on a graph. You can encounter these kind of graph coloring examples in children's coloring book, where each vertex or layer of the drawing indicates what color should be used to have a good coloring. So let's talk about, lastly, the region coloring. Region coloring is an assignment of colors to the regions of a planar graph such that no two adjacent regions have the same color. Two regions are said to be adjacent if they have common edge. The best example here is the world map. As you can see, the assignment of the colors in each country that uses only 4 colors, or what we call the 4 coloring problem. After all we've been through, let's have a basic world problem. Let's talk about the game Sudoku. Sudoku is a mini puzzle game which graph coloring can also be used. Filling the blanks using only logic while paying attention not to repeat a digit in the same row or column. Each Sudoku puzzle has only one possible solution. The numbers allocated at the beginning of each puzzle are the clues to unveil it. No guessing is allowed. Sudoku is a game of logic. So, after answering the puzzle, we can also provide a coloring in each number on every cell. It's based on what color you are going to use unless you are not repeating the same color in every column and rows. The equation to know the number of colors in this game can be written as the chromatic number of the graph is equal to chromatic. By solving it, we will count the number of colors or the numbers used in this puzzle. Then after counting it, we can say that this puzzle is a 4 coloring, or the minimum coloring of the game Sudoku is 4. So let's have a real world problem. Exporting heavily contributes to the economic growth of a country, largely by boosting the productivity of firms. Canada does this effectively. Hence, firms there have significantly higher productivity than firms that do not export. Canada has a great trade relations with Asian countries, specifically Japan. This relationship is beneficial to both parties as they share common innovation objectives. Japan is Canada's 4th largest trading partner with $29.3 billion in bilateral merchandise trade in 2017. You can see in the graph, we replace the edges by indicating it by the resources exporting in different countries. In this figure number 2, we replace the vertex by the countries exporting each other. After analyzing the graph, here's the detailed interpretation of it. So I therefore conclude that graphs, vertices, edges, and colors can help in our everyday living. The main goal of the graph theory is to help us to distinguish and to generate most fastest and easiest way to solve a specific problem.